Okay, so we're going to start with this is a record player, and you're looking at it from the side. Notice it says, I have a little spinny indicator there at the top, and it says omega equals 33 RPMs. Yes, indeed, in the old days, long before CDs and certainly before digital versions of ability to play music, we would put these records, they were skinny, thin discs, on a record player. There was a little needle, and it would be set in the grooves on the record, and then those vibrations would actually be, translated to something that you could hear in the form of music. The records came in two basic, and then there was a third less common size. Bigger records, which had a diameter of about 13 inches, spun at 33 RPMs. Then there were singles that you could buy, and they were smaller, and they spun at 45 RPMs. Have you ever heard of, 45? No. Okay. So the singles, if you wanted to buy, those were like the top hits, and you would buy it on one side, you'd have a really popular song, and on the other side was some obscure song that the artist was trying to, make into a popular song. The question, though, is why would the smaller record need to spin faster than the bigger record? Melissa?
How much it would be would need to vibrate. I don't know.
You're on the right track.
Because the larger one, it's bigger around, so the slower it would go, it would be, I don't know, it would be more deep. It makes sense in my head.
Go ahead, Varun.
So because the radius is smaller, it has to spin faster. So what I actually said, with the bigger one, you had more space to put the music in. So it'll require less speed. But since it's more compact, you need to go faster, so the music sounds, consistent and normal.
Right. The smaller the circle, go ahead, Travis.
Is there the same amount of songs and playtime on each?
Oh no, the 33s had that was a whole album.
Oh, so
there might be
just a song?
Yes, that's correct.
Okay.
Yeah, that's correct. So if you're down at the carousel, and I'm going to give you some extra credit opportunities here. If you're down at the carousel and you're riding one of the inside horses, why is that less fun than riding one on the outside? Yeah, you're not going as fast, right? So for extra credit, go down to the carousel and figure out how fast the horses on the outside are traveling.
Can we do it with the GPS?
I'm kind of ask them question.
That would be cheating. That would suck all the fun out, Travis.
That'd be efficient.
Per minute?
Why are you mad?
Yeah, how are you going to do that? How are you going to figure out how fast? And I want to know how fast in miles per hour. How fast is the outside horse traveling?
So
Nate, go. Yeah, so try to pick a time when it's moving at a constant speed, once it's kind of revved up. You're right about that. Yep. So how would you do this? How'd you figure out how fast those horsies were going? Travis?
You can mark out one horse and just wait for it to go all the way around, and then stop the stopwatch, and then measure the radius from the inside horses and the outside horses, and compare them. You have to figure out the area.
Yeah, you'll have to figure out how big the circle is, right? So Travis is right. If you time, once it gets going, like Nathan said, you want to get it time to accelerate, get up to speed, right? Figure out how much time it takes to go around once, then you're going to have to figure out how big that circle is. Instruction or custodial? Oh, it's Joe. So how are you going to figure out how big a circle the merry-go-round makes?
Easy.
Let's go.
Okay, well, first of all, you have to take into consideration the middle column. So you get the circumference of the middle column, solve for the radius, and then you just measure from the middle column to the outside while the thing is spinning.
I don't know.
Radius to that.
So how are you going to figure out the circumference of that middle column?
Also, you have the radius, just solve for circumference.
How are you going to know the radius of that middle column? I know what you're talking about. You can't go right to the center of the merry-go-round, correct?
You take a tape measure, and you measure the circumference, and
Okay.
solve for the radius.
Okay.
Start the measuring from the middle column to the outside, and you take that radius and add it.
Okay. Does everybody follow Travis's? And I don't know if you have a tape measure that's big enough to get around that central sort of column.
I do.
You could use some string or rope or something like that, yeah. I doubt that they know. I doubt they've done the math. But here's, for extra credit, compare how fast our carousel is going to the one in Missoula, Montana. There's a carousel in Missoula, Montana. So that one you just have to look up. I've actually ridden that carousel, and it feels like it's screaming, like it's going really fast. So I'm just curious, like, if we compared ours to the one in Missoula, if it was just me, and like, I don't know, it was a long time ago, was I just like...
Where is that? Like, if this is Montana.
Okay, it's on the west side, Missoula, and it's up on the mountain.
Okay, that happens.
M-I-Zula. I think it's got S's instead of Z's. M-I-S-S-O-U-L-A. I'm thinking. All right. So, let's solve this question here. We have a cockroach sitting on the edge of a 13-inch diameter record player. And I want to know, how sticky do his feet have to be so that he doesn't fly off the record when it's going at its normal 33 RPM? Yeah, the needle's got a little bit of an issue there. So he's right on the edge. He's missed the needle. And I'm going to do this one for you. Now, centripetal forces, listen please. Centripetal forces are always equated to some other force. So for, like, the Earth revolving around the sun, what produces the centripetal force that holds it in orbit? Gravity. Gravity from the sun. So here, friction is the centripetal force that holds the cockroach on the record. Friction is mu times the normal. What's the normal force for this picture? mg, good. And the centripetal force is mv squared over r. Now, since this is in angular terms, RPMs, I'm going to use, if you look at the board where it's the maroon value or equations, see how it says omega equals v over r? I'm going to use that, and I'm going to substitute for v so we don't have to, like, do some converting. So omega equals v over r, and v equals omega times r. So I'm going to take that, and bam, put it right there, and we'll end up with mu mg equals m omega squared r squared over r. And by the way, that is where we got the second equation for centripetal force, which is in blue. Notice it's m omega squared times r. Okay? So besides the r, what else cancels? Mass, right. Not omega, sorry, my bad. So this equation, if we're going to solve for mu, ends up becoming mu equals omega squared times r divided by gravity. The W didn't, I just crossed the wrong thing out. Now we just have to make sure that the units here are all matching. What are the units for omega? We did this yesterday. What are they? Radians per second. And right now, we're currently in RPM. So we're going to have to do some converting there. What's the radius currently in? Inches. And gravity? Gravity is in what units? Yeah, so we gotta do some converting here. Let's start with omega. 33, what's RPM stand for? Revolutions or rotations per what? Minute. That's what the M is for, yeah. So we're going to convert that to radians per second. 1 minute is 60 seconds. I think you probably know it.
Divided by pi.
Mm-hmm. Yeah. So how many radians are there in one revolution?
2 pi.
2 pi.
Like algebra 2 math?
Yes.
Failed that class, man.
So now you've got radians per second. If I solve that, I get 3.46. Okay, so that one's good. And then I have to match gravity and the radius. So right now we're in inches. We know gravity either in feet or meters. So which one would you like to convert? Do you want to convert this to feet?
That's easy, just divide by 12.
Yeah, you could do that. You could just divide that by 12 and you get, so cut it in half and then divide by 12 because we need the radius, right? So the radius will be, yep, 6.5 inches, and there's 12 inches in a foot. So the radius is 0.542. Keep an extra sig fig around. Feet. So now I got everything I need. Mu will equal angular speed squared, 3.46 squared.
Find that gravity in theater.
I just know gravity in feet per second squared. It is 32, yeah. 32.2 to be exact. So that's our radius in feet. And then I'm going to divide it by 32 feet per second squared. So those units all match. Radians per second, feet, and feet per square second. When I do that, actually get a reasonable answer. 0.20. Okay? All righty. So now I'm going to